In this tutorial, we'll be talking about unsupervised learning. So up till this point, we've been talking about supervised learning. So this is a good time to kind of discuss the different types of machine learning. Um, machine learning. Okay, and what we've been talking about so far is supervised machine learning. And what supervised means is basically the setup that we've been working with, which is you have xi, yi pairs. Okay, so for each data input xi, you have a target or output variable yi, and you try to learn the relationship between the x's and the y's. So this is everything we've done: linear regression, logistic regression, classification. All of those things have been supervised because we're always dealing with the case where our input is labeled or it has targets. Unsupervised, okay, is slightly different. It's we just have xi's. Okay, so we don't actually know, we don't actually know the target. We don't know what we're looking for really. So some examples of this are clustering, or the most famous example is clustering. Okay, so clustering. So for example, you see a bunch of data points. This is obviously a very trivial example here. So I see data points like this, and you're basically asked to find some kind of structure in the data. So one structure you could find is to say, well, okay, these points here seem to belong to a cluster. These points here belong to a cluster, and the third set of points belongs to a cluster here. Now this is really obvious. Any clustering algorithm will figure this out. Even we can just kind of eyeball it and see. It's pretty obvious what the clusters should be. Other types of clustering, for example, you could have data like this. Okay, and this could be, how do you cluster this thing? Well, there's no right or wrong answer, right? Some clustering algorithms might give you an answer that looks like this. So I'm just drawing my two clusters in different shapes. Some algorithms will notice the shape. And give you these two clusters. And so, depending on the type of clustering algorithm you use, you'll end up with different clusters. And kind of the hard part about unsupervised learning is, how do you know what a good outcome is? Because you don't have these yi's to tell you what your loss is, so you don't really have anything you can work with in terms of evaluating how good your results are. And so that's kind of the beauty and the difficulty of unsupervised learning. You're basically tasked with trying to find some kind of structure in the data. Today, I guess we'll be talking about two ideas. The first one is principal component analysis. Okay, so PCA, and the second one is k-means clustering. Okay, and I'll spend most of my time talking about PCA because it's really interesting. K-means is the most simple clustering algorithm. Principal component analysis is kind of a, the way I like to think about it is it's a way of dimensionality reduction. Okay, so the way principal component analysis works, and we'll talk about this a lot, is that we have some kind of high dimensional data set, so lots of features, and we try to summarize the data in a smaller number of features. So this comes up a lot, for example, in image data. Okay, what is an image? Well, an image is a grid or a matrix. Okay, and let's say we have P, so this is P rows, P columns. Each one of these guys is a pixel, so each grid is a pixel. A pixel is a number between, let's say, 0 and 1. You can normalize it to be anything you want. Okay, and so one image, let's say, this is an image of a cat. It looks like this. One image, let's call this xi. This is a p squared. So if we were going to flatten this image out, so this is a p by p image, right? But if we were going to think of this as a vector, right, each data point is usually thought of as a vector. If we thought of this as a vector, then this would be a p squared times 1 vector. Okay, so p squared for high quality images can be massive, right? So even when we're talking about MNIST, which we'll actually deal with in this tutorial, this is kind of a really simple data set. You're still talking about massive number of features. So number of features, say greater than 500. And so this kind of motivates the idea of the need for dimensionality reduction, right? Because do we really believe that pictures of cats live in a p squared? So let's say, for example, let's just say p is equal to 1,000, right? You can have a very high quality image of cats that's 1,000 by 1,000. So the question is, do you really believe that an image of a cat lives in a 10,000 dimensional space? Do we need 10,000 dimensions to kind of try to explain or understand that the image is an image of a cat? And the answer is no. We can actually simplify, we can reduce the dimension and try to compress the information in 1,000 by 1,000 image in a much smaller image. Okay, so let me start off by drawing the picture that I'm sure you've seen before. Every time you Google PCA, this is the image that comes up. But I want to try to explain it in more detail. So PCA motivation. All right, so let's just imagine that we had. So this is a 2D problem. Okay, obviously, if you're working in 2 dimensions, you don't really care about dimensionality reduction. So I'm just using this idea as a motivation, and you can kind of picture this in a much higher dimensional space. So let's say we have data, and let's say this data looks, let's see, something like this. Okay, and let me just make a copy of this. Okay, so we have the same data set. And this is x1, x2, x1, x2. Okay, so my question is, or what I want to kind of illustrate is, let's say you had the following line that looks like this. And let's say on this one you had this line. Okay. Now think of projecting each of the data points onto the line in each image. So in this case, this point here, right? Let me draw it in bright red. This point here would get projected. So I'm talking, when I say projection, I mean orthogonal projection, meaning that I want there to be a right angle between where, the line that connects the point to the black line. Okay, and so let me see this point projected onto the line. So now we have these 2 points. This point gets projected here. Okay, and I'm going to do this for all the points. Okay, so this line, if we kind of picture this line drawn out flat, and we picture the points on the line, what we see is 2 points next to each other here, 2 points next to each other here, and 2 points slightly far away from each other here. Okay, so what I'm doing is taking this black line and just looking at it in one dimension. So basically here we have a 2-dimensional problem, and what I'm trying to do is projecting the data in 2 dimensions onto a single dimension, right? Dimensional reduction, we're going down in dimension. And in the 1-dimensional data set, okay, the projection of these 2-dimensional points onto this particular axis looks like this, okay? Now, this is another axis we could pick, right? You could pick any axis, and when I say axis, I mean any black line in the 2-dimensional space, right? We can pick any kind of axis and try to figure out what the points look like when they're projected onto that axis. Now here, we do the same thing, we project the points. Okay, and so here what we see is, so now we're projecting onto 1 dimension. So in the 1D world, here we'll see points more spread out. Okay, so what I want you to notice is the first axis here, okay, the variance is lower, right? And when I say variance, I'm looking at the spread. So the spread of the points is lower. If you look at the spread here, it's much bigger, right? The spread of the points are much more spread out, right? And so if you were trying to project your 2-dimensional data set onto a 1-dimensional subset or subspace, which one would you prefer? And the answer is you would prefer this one, right? Because what you want is to be able to differentiate between 2 different values. So if you project down to a subspace, you want to be able to preserve some kind of separation between the data. Whereas here, right, the data looks more and more similar. Another way to see this is that if you're trying to pick features in your data set, let's say you have 10 features, features that have higher variance are more likely to be features that let you distinguish between different examples and let you kind of do a better job at prediction. So the idea of principal components is you can take a p-dimensional data set and find the p, so compute the p principal components, okay? And hopefully, so when I say principal components, I mean, so actually let me, which are the axes on which variance is maximized. Okay, and then we pick a subset, let's say M, which is smaller than P, to summarize the data. Okay, now I'm going to make this much more concrete, but this is basically the motivation for what we're trying to do. Now, if you look at this line here, right? What is this? What is this line, the black line here? Well, this is the line. So I kind of drew it a little bit wonky. I wanted it to go through the origin. So just imagine it's going through the origin. This is the line x2 equals to x1. Okay, and this is the line x2 equals negative x1. Okay, and so another way of writing this is x2 minus x1 equals to 0. This is x2 plus x1 equals to 0. So what we're actually doing is finding axes that are a combination, a linear combination of the two features, right? And here x2 plus x1 is a combination of the two features. So the principal components are going to be linear combinations of the dimensions in your data set. And we're going to try to find the best one in terms of the one that maximizes variance. Okay, so just keep this in mind. I'm going to come back and talk about this some more. Before I do that, I want to talk about eigenvalues. And eigenvectors of matrices. Okay, and it turns out that eigenvectors are, well, we're going to need eigenvalues and eigenvectors to be able to derive principal components. And it turns out that the eigenvectors of a special kind of matrix actually gives you the principal components. So before we talk about this, let's just kind of review what a matrix is, right? So let's say you have a matrix that's m by n dimensional. So what that means is that if you have a vector in Rn and you compute Ax equals b, right? Then b is a vector in Rm. Okay. Now, so you can view a matrix A as a function or as a map that maps vectors in Rn to vectors in Rm, right? Because look at what this is doing, right? A is just a function. It takes an input x, which is the n-dimensional vector, and it maps it to some vector b, which is m-dimensional. So you can think of the matrix A itself as an operator that operates on the space Rn and ends up in Rm. Okay. Now, I've just drawn, using Python here, a matrix multiplication example just to kind of solidify some of the ideas I want to talk about. So here I've got this matrix, this 2 by 2 matrix, which is really simple. And basically, I just want to describe what this matrix is actually doing. So here I've drawn the vectors 0, 1. So this one is 0, 1. This one is 1, 0. And this one is the vector 1, 1. And I basically want to apply the matrix A, right? I want to take this matrix A and show you what it does to this square, right? Each of these squares is a vector. I'm only highlighting 3 of them, but each of the points in this square are a vector. And I want to apply A to every single vector, okay? So let's see what that gives us. So here I'm just taking the multiplication of A with each of those vectors. Okay, and I'm going to draw it out now. And we get this. Okay, so basically what the matrix A is doing is taking this vector here and mapping it to this vector here. So it's basically tilting it to the right and stretching it out a little bit. Same thing here for the 1, 1 vector. It's tilting it to the right and stretching it out a little bit. What's interesting is this vector here, right? The vector 0, 1, it doesn't get tilted. It just gets stretched, right? So the direction of 1, 1 doesn't change. All that changes is the stretching factor. So it just gets stretched out. And this is what we call an eigenvector of A. Okay, so if you recall, perhaps from high school or other courses you've done, an eigenvector X of matrix A satisfies AX equals to lambda X. And we call lambda and X an eigenpair. Okay, and lambda is called an eigenvalue. So what does this mean, right? Well, we just saw that when we take, so we had this kind of picture, right? And we saw that when we take the matrix A and apply it to this particular vector, what we get is a vector that's slightly longer, right? So the result of AX is the original vector multiplied by some factor lambda, right? This is just a number. So what happens when I have X and then I have 2X, right? All that happens is it gets stretched out. So here we just have some lambda, maybe lambda is equal to like 1.3, for example. It just gets stretched out a little bit. So the effect of A on X is just to not change its direction, but to stretch it out or shrink it, right? So if lambda is less than 1, it shrinks it. If it's greater than 1, it elongates it. Okay, now if you wanted to find all the eigenvalues of A, NumPy has a nice function called linalg.eig. So here it gives me the eigenvalues. Maybe I should make this clearer. Well, actually, I'll just call them L and V. So L is the eigenvalues, V is the eigenvectors. And we can see here that the eigenvectors of A are the vectors 1, 0, right? So the first column, 1, 0, and the second eigenvector is negative 0.9, 0.3, okay, which I haven't plotted here, but is also an eigenvector. We can look at the eigenvalues, okay, and it's telling us that the eigenvalues are 1.4 and 1.2. So this eigenvalue corresponds to this eigenvector, right? That's really important. So every eigenvector has a corresponding eigenvalue, and you know, so here we're getting 2 eigenvectors, 2 eigenvalues, and we can see that the eigenvalue is 1.4. So you can see that we're basically taking the black original vector and we're multiplying it by 1.4. So we're stretching it out to the red resulting vector. Okay, and it turns out that these eigenvectors are really important because they give you a direction that tells you something particularly important about the matrix. And when we're talking about data, it actually gives you the direction of greatest variance. Okay, and we're going to talk about that a lot. But if you kind of contrast, if you go back to this idea that I was talking about here, when we're looking for this black line, we're looking for directions. And the direction that we really want is the direction that maximizes the variance. Okay, and it turns out that those directions are actually the eigenvectors. And the variance is actually equal to the eigenvalue. So we'll see that in a minute. So before I jump into actually talking about data, what I want to talk about, what I want to show is a concrete example of computing eigenvalues. Okay, so I know this might be, if you haven't done eigenvalues before, this might be, you know, a lot to take in. So you know, if you haven't, please do a quick review online of eigenvalues, but I'm just going to go ahead and walk through an example of how to compute eigenvalues and eigenvectors. So I'm going to look at this particular example where we have a 2 by 2 dimensional matrix. Okay, and so I should say only square matrices have eigenvalues and eigenvectors. Okay, if we are talking about non-square matrices or rectangular matrices, we usually talk about the singular value decomposition, which kind of is a generalization. Okay, so here we're only talking about square matrices. Only square matrices have eigenvalues, and the number of eigenvalues is going to be equal to the dimension. So this is a 2 by 2 matrix, so it's going to have 2 eigenvalues. Okay, two eigenvectors. So we know that we need to compute, or we need to find an eigenvector and an eigenvalue such that this is satisfied. Okay, and usually the way we do this is we rewrite this as ax minus lambda x equals to 0, which is the same as writing a minus lambda times the identity x equals to 0. Okay, so you can see from here to here, all I'm doing is just taking the x in common. And this condition here, you can review your linear algebra, but basically this is the same as requiring that the determinant of a minus lambda I equals to 0. Okay, so remember, determinant for a 2 by 2 matrix is really easy to compute. So determinant of a 2 by 2 matrix, A, B, C, D, is just AD minus BC. Okay, so let's apply this to this matrix. So the determinant of A minus lambda I is the determinant of the matrix 0, 1, negative 2, negative 3, minus lambda times identity. Well, that's just lambda on the diagonals and 0 elsewhere. And that's going to be, well, let's look at the first component, 0 minus lambda. So we'll get negative lambda, 1, negative 2, and negative 3 minus lambda. And using this formula up here, negative lambda times negative 3 minus lambda is lambda 3 plus lambda, minus 1 times negative 2, that's plus 2. And this is equal to lambda squared plus 3 lambda plus 2. Okay, and remember what we're trying to solve. We're trying to solve for the determinant equals 0. So we need to solve for lambda that satisfies, so satisfying lambda squared plus 3 lambda plus 2 equals 0. Okay, now hopefully you remember what this kind of equation is. This is a quadratic equation. Okay, and they're really easy to solve. And in this case, I won't walk you through it. You can actually find that lambda 1, remember we have two eigenvalues. There's going to be two equations to this. This is a quadratic equation, so this is going to be a parabola that looks like this. There's going to be two places where it hits the x-axis, so the 0, and those two values are going to be the eigenvalues of this matrix. And it turns out that lambda 1 is equal to negative 2, and lambda 2 is equal to negative 1. And just to note, usually we order the eigenvalues in decreasing size of absolute value. Okay, so negative 2, absolute value is 2, negative 1, absolute value is 1, so 2 is bigger than 1. So we take the bigger one to be the first eigenvalue, okay, and we take the smaller one to be the second eigenvalue. So that's pretty important for our purposes. We need to keep this in mind. And we have the eigenvalues. We need to find the eigenvectors. So we can start off by looking at the eigenvector for lambda 1 equals negative 2. So we need to find a eigenvector x1 which satisfies this equation, negative 2x1, right? Ax equals lambda x, and we know that lambda is negative 2. So we need to solve this. We need to find this x. So what is a? Well, it's going to be 0, 1, negative 2, negative 3. What's x1? Well, we can just write that as the two components, x1, x1, 2. And here we can write that as x1, 1, x1, 2. Okay, and if I do the matrix multiplication, I'll get 0 times x11 plus 1 times x12. So let me do it here. So I'll get x12 is equal to negative 2 x11 Okay, that's the first equation. And the second equation is minus 2x11 minus 3x12 is equal to minus 2x12. This is the second equation. So you can see all I'm doing is multiplying this row by this column equals to the first component on the right, and similarly for the second row. Now actually all we need is the first bit. Okay, this is basically telling me that the vector x1 has to satisfy this relationship between its two elements. Okay, so what this is saying is that the first element times -2 has to be the second element. So what I can just pick is, say the first element is 1, then the second element must be -2 times 1. Okay, so this is an eigenvector of this matrix A, and let's just check that. So A x1 is going to be, so 0, so it's going to be -2, and multiply the second row by this column, we'll get -2 plus 6, so 4. And this is just going to be equal to -2. Okay, so you can see that this is the eigenvalue that we're looking for, and this is exactly or precisely the eigenvector. Now, we actually have a problem here, a bit of a problem, that I can just pick this arbitrarily, right? I could also have picked x1 to be, I could have picked it to be, say, 2, right? And then in this case, x12 would have to be -4, right? Same thing. You know, if you check it out, if you check this out, you'll get ax1 equals to -2 times the vector. This is not telling me what x11 has to be. I can pick that to be anything, and x12 just has to satisfy this property here. And similarly, I could also have picked x1 to be -1, 2. This will also satisfy this equation because x11 times -2 would be 2. So this is also true. Okay, so what do we do? The usual way to do this is to take the eigenvector is the norm 1 vector satisfying the requirement. Okay, that means that we want the length of the vector to be 1, and that gives us a way of having a unique eigenvector. So what is the length of x1? Well, it's going to be the square root of 1 squared plus -2 squared, so that's square root of 5, okay? And so we can take x1 to be equals to 1 over square root of 5 minus 2 over square root of 5. Now you should check for yourself that if you look at the length of x1 now, it's actually going to be just a length 1 vector. Okay, and you can check that also if you take the length of this one, here you'll get square root of 2 squared plus 4 squared, so that's square root of 20. And if you divide those elements by square root of 20, you'll get the same vector here. Okay, and okay, that looks right to me. So this is our eigenvector, and for lambda 2, which was -1, we can do the same calculation. I won't do it because it's exactly the same. We'll get 1 over root 2, -1 over root 2. Okay, so for this vector, we've got the two eigenvectors, x1 and x2. Okay, and that kind of concludes the example that I wanted to go through. It's not really important to be able to do this by hand, but I just wanted to show you that it's not, it's nothing too difficult. All right, so let's talk again about principal components. Okay, so the setup in PCA is that we have a set of data. Let's call it set of, actually let me just call it a sample of n data points. Okay, and we'll call them x1 to xn, and each xi is a p-dimensional vector. Okay, so it's a feature. It's a vector of p features. Okay, and we have n examples in our sample. Now, just to add to the notation, we have x bar is just going to be equal to 1 over n times the sum of the xi. So x bar is also a vector in p dimensions. Okay, but it's going to be the sum or the average of the n vectors. And okay, so here's our sample of n data points. Each data point is a p-dimensional vector, and we have the sample average x bar is a vector as well. And let's just assume we want to find the first PC. So I want to project the data from the p-dimensional space down to the one-dimensional space. Okay, so how do I do that? Well, to project a point, a vector in p dimensions down to one vector, I need to have a vector, let's call it alpha, and let's call it alpha 1 because we're talking about the first principal component, which is going to be a vector alpha 1 1, alpha 1 2, alpha 1 p. So this is a p-dimensional vector, and therefore alpha 1 transpose times x1, so the dot product of alpha 1 and one of the data points, any of the data points, let's call it xi, is going to be just a number, right, in R1. So the projection down of a p-dimensional vector to a one-dimensional space, we need to find another p-dimensional vector, multiply them together to get a single number. So you can see that alpha 1, if you take the dot product with any of these points, you move them from being p-dimensional in p-dimensional space down to one-dimensional space. The question is, how do we pick alpha or alpha 1? Well, we want the variance of the projected data to be maximized. Okay, so this goes back to the picture I drew here. We have projections of the two-dimensional data set down to a single dimension, right? But we prefer the projection that gives us a higher variance. Okay, so how do we compute the variance of the points? How do we compute the variance of the points here, right? So how do we compute variance? Remember, sample variance is 1 over n minus 1 times the sum of xi minus x bar squared. Okay, so how are we going to compute the variance here? Well, the variance here is going to be similar, except we're going to be talking about matrices. So what is our xi? It's the projected point, alpha 1 transpose xi, minus the mean, which is just this value that we computed up here. I should clarify, this should be the mean projected down to the original point. Okay, and just to make this really clear, if I project, let me put it up here, if I project each xi down to alpha 1 transpose xi, then what is the mean of the new vectors? It's going to be 1 over n times the sum of alpha 1 transpose xi, right? This alpha 1 can be taken outside of the summation because there's no index and everything is linear. So this becomes alpha 1 transpose 1 over n xi, which is alpha 1 transpose x bar n. Okay, so here, when we're looking at the variance of the projected points, we look at each point. Each point now is alpha 1 transpose xi. minus the mean of all the points, which is alpha 1 transpose x bar. And we square it just like in the, sorry, this should be n minus 1, and we square it just like in the previous case. Now, you can actually rewrite this as alpha 1 transpose times 1 over n minus 1 alpha 1. Okay, so I won't prove this, but you can kind of convince yourself that these two things are the same. I take the alpha 1 because we have a square, we have this squared term. You can take the alpha 1 out the front and out the back here, so we get this expression. The reason I want to get this expression is this guy here is actually called S. This is the sample covariance matrix. Okay, so this is the matrix of covariances between the xi's. Okay, and this is a really important quantity. It's the sample covariance because it's based on the sample. It's not the true covariance. Okay, we don't have access to the true covariance. But basically, what we're trying to do is we're trying to find this alpha vector that projects the data down. So it's a p-dimensional vector such that we maximize this value alpha 1 transpose S alpha 1. Okay. So let me write it here on a new page. Okay, on a new page. Okay, we want to find alpha 1 in p dimensions such that alpha 1 transpose S alpha 1 is maximized where S is the sample covariance matrix of the data points x1 to n. Okay, so some of you will look at this problem and say, well, it's really easy because we can always take alpha 1 to be infinite, right? Because to maximize this quantity, if you take the alpha 1s bigger and bigger, you'll maximize, you'll keep getting a bigger and bigger value for this thing. Okay, so we actually need a constraint. Okay, and the constraint is usually taken to be that alpha transpose 1, alpha 1 is equal to 1. Okay, another way of saying that is that the length of alpha 1 is just equal to 1. Hopefully you can see the reason we need this. If you're allowed to pick any alpha 1 you want, right, you can keep picking it so that this thing keeps getting bigger and bigger and bigger until you get to infinity. So that's not a valid solution. So we need some constraint on the alpha 1 to be able to solve this problem. So hopefully you remember from the SVM tutorial, how do we solve things like this? Well, we want to maximize something subject to a constraint here, okay? And the way we do that is we set up the Lagrangian. Okay, and the Lagrangian is a function of the variable we're trying to maximize with respect to, and a Lagrange variable, we'll call it lambda. And the way this works is that it's the original function, okay, minus the constraint. Okay, and usually, if you recall, we take the constraint and we write it so that it's something equals 0. Okay, so this is the constraint, this is the Lagrange variable. So we have this quantity, and then to solve this, we can compute the derivative with respect to the first variable. Now the derivative of this guy, this is just a quadratic in alpha 1, so this is going to be 2s alpha 1. Okay, so if you're confused by this, you can check out the Wikipedia matrix calculus page or first linear regression tutorial where we kind of dealt with derivatives of this kind. And then to take the derivative here, this is a quadratic again, so this is going to be minus 2 lambda alpha 1, and we set it equal to 0. Okay, and now if you rearrange, you can cancel out the 2's, and what you'll see is that what we get is s alpha 1 equals to lambda alpha 1. Okay, and just pause the video here and try to figure what this is actually telling us. It's telling us that alpha 1, right, is the vector that satisfies this kind of property for the matrix S. Okay, and hopefully you can kind of connect this with what we talked about earlier. Alpha 1 is an eigenvector of S with eigenvalue lambda. Right? Only eigenvectors satisfy this condition, so alpha 1 must be an eigenvector of S. Now, the question is, which eigenvector is it, right? Because we have how many? We have, if you recall from the definition of S, right? It's this quantity. So this is going to be, so xi is a p by 1 vector. Xi minus x bar is a p by 1 vector. This xi minus x bar transpose is a 1 by p vector. So S is a p by p, right? P by 1 times 1 minus 1 by p is p by p. So this is a p by p dimensional matrix, and so it's going to have p eigenvectors. And the question is, which eigenvector is this particular thing considering? Well, since we want to maximize the variance, right? What is this quantity here? Well, this quantity here, alpha 1 transpose S alpha 1 is equal to alpha 1 transpose, so S alpha 1, we can use the result here to write it as lambda alpha 1. And so this is equal to lambda alpha 1 transpose alpha 1, right? Lambda is just a number, you can just take it outside of this. And this is equal to lambda because, remember, the constraint that we put down was that this thing is equal to 1. So maximizing the variance is the same as maximizing lambda. And we know that the lambdas are ordered in decreasing order, right? And so this has to be lambda 1, right? The biggest eigenvalue. Okay, now it's kind of a subtle point. I didn't really talk about it. We can have negative eigenvalues. So in theory, this could be a negative value, but because this is a covariance matrix, we're always going to get positive eigenvalues. And so lambda 1 will actually be the largest eigenvalue. And it's actually giving us the variance of the projected points. Okay, so lambda 1 is actually the variance that's captured on this first axis, and the axis itself is given by the vector alpha 1, right? And that is actually our first principal component, okay? So again, alpha 1 is giving us a projection onto a one-dimensional space. The variance of the points on this one-dimensional space is equal to lambda 1, okay? So if we go back to our original picture, the projection of the points here, right? The best projection in terms of the one that maximizes the variance is given by the first eigenvector, okay, of the points. The first eigenvector of the sample covariance of the points. And the variance, right, this number here of the points on the new space is equal to the first eigenvalue. Okay, and so that is the connection between principal components and eigenvalues. Now, usually, you know, we don't just want we don't usually want a single eigenvector, or we don't want a single principal component. We want multiple eigen um, or multiple principal components. So what is the second principal component? Well, that's going to be another vector. We'll call it alpha2, which is a p-dimensional vector, where alpha2 maximizes the variance. So again, I'm not going to show the computation again, but we're going to get the same variance except with alpha2 now, such that we still need the constraint that this is equal to 1 for the same reason as before. Okay, but we're going to actually have an extra condition. So alpha2 is projecting onto another one-dimensional subspace, but we want the second direction or axis to be orthogonal to the first direction that we found. Okay, so in that first example that I drew, if this is your first principal component, the second principal component has to be orthogonal to this one, meaning it has to be there has to be a 90-degree angle here. In 2 dimensions, this is not very interesting because, of course, if you figure out one principal component, finding out the orthogonal direction is really just trivial, right? There's no need for a maximization. You can actually just just compute something orthogonal. But in higher dimensions, in p dimensions, after you find the first principal component, then you have p minus 1 directions to look at that are going to be orthogonal to the first one, right? So there's the number of orthogonal directions in higher dimensional spaces is larger. Okay, so this really, you should think about this in p-dimensional space. But in terms of the math, we want to maximize the variance. We still want the projection vector to be have norm 1, and we want the second direction to be orthogonal to the first. And the way we encode this is that the dot product of the 2 vectors is actually 0. Okay, that actually, remember from the discussion of dot product between vectors in the classification tutorial and also during the perceptron tutorial, we get orthogonality by requiring dot products to be 0. Okay, so now let's actually solve for alpha2, but now we're going to have 2 constraints, right? This one and this one. And I'm going to use a different, this is a different lambda to before, but I'll still call it lambda. And we're going to have two Lagrange variables because we have 2 constraints. And this is equal to alpha2 transpose S alpha2 minus the first condition. And then we also want to minus the second condition. The second condition is just phi times alpha1 transpose alpha2. Okay, so this is already in the form something equals to 0. So we get this Lagrangian. Again, I take the derivative with respect to alpha2. I'll get 2 S alpha2 minus 2 lambda alpha2 minus phi alpha1. And we want to make this equal to 0. Okay, now there's a little bit of a trick here. The trick is to multiply both sides by alpha1 transpose. Okay, so we want to multiply both sides by alpha1 transpose. The reason I can do that is because this side is just 0, so I'll just still get 0 here. Okay, but what ends up happening is that we get 2 alpha1 transpose S lambda alpha1 transpose alpha2 and minus phi alpha1 transpose alpha1 equals to 0. Okay, now we have to slightly rearrange Okay, what is alpha 1 transpose S? Well, we can actually rewrite this guy as 2 alpha 2 transpose S alpha 1 minus 2 lambda alpha 1 transpose alpha 2. Okay, so these two guys are equal. I'm just, because S is symmetric, I can switch these around. And what I want to note is that this guy, S alpha 1, right? If we look back to here, S alpha 1 is equal to lambda alpha 1. And let me just be careful, it's not the same lambda as here. I'll call this lambda 1, alpha 1, minus 2, lambda alpha 1 transpose alpha 2, minus phi. Okay, now this lambda 1 is just a constant. I can take it outside, and what do I get? I get alpha 2 transpose alpha 1. So this guy is equal to 0, because that was one of the conditions, right? Alpha 1 transpose alpha 2 is equal to 0. And similarly here, I also get alpha 1 transpose alpha 2, so this is also equal to 0. So what that tells me is that this guy is minus phi alpha 1 transpose alpha 1 equals to 0. That must be, then that must tell us that phi is equal to 0, because alpha 1 transpose alpha 1, that's just equal to 1. So we end up with negative phi equals 0, so phi is equal to 0. Okay, so plugging phi equals 0 back into what we got initially, this derivative. Okay, so we'll get 2s alpha 2 minus 2 lambda alpha 2 equals 0, right? Because this guy is just 0. Then I can rearrange a little bit to get s alpha 2 equals lambda alpha 2. And so again, you should hopefully see that this means that alpha 2 is an eigenvector of S with eigenvalue lambda. Okay, which eigenvalue eigenvector pair is this? Well, hopefully you can see that this has to be the largest one, such that it's still orthogonal to the first one, and so it can't be the first one. So it has to be the second eigenvector pair, because the eigenvalues are ordered in decreasing order. Okay, so in general, and sorry, so I should say, just to be really clear, the variance on this captured on the second principal component is equal to lambda 2, right? Because lambda 2 is equal to, so what is the variance on the second principal component? It's this, which is just equal to, so S alpha 2 is lambda 2 alpha 2. So this is equal to lambda 2, just like before. And so the variance on the second principal component is the second eigenvalue. So you can see that the eigenvalues are actually giving you the variance explained by each principal component. Okay? So what that means is that if you can figure out the eigenvalues of the covariance matrix, right, and you look at the, say, the first 5 principal components, okay, and you look at the first 5 eigenvalues, and they explain 70% of the total variance in the data, then you might be able to get away with just looking at the first 5 principal components of your data set rather than the entirety of the data set. So this is the idea of featured reduction, because we are trying to summarize a p-dimensional thing in a much smaller number of principal components and just using those to do our machine learning with. And it's much easier to work in a lower dimensional space. Okay. So let's actually see a concrete example of that in the lab this week. Okay, so the lab this week is based on a pretty good book, actually, with a lot of good examples. So it's this Python Data Science Handbook by Jake Vanderplas. It's actually all available on GitHub, so a lot of the labs for this course are actually based on this book. I don't usually go through labs because I think the best way to learn a lot of this stuff is to just go through it on your own. So I try to talk about the theory. But for this particular topic, it's really nice to look at how principal components work on data, in particular image data. So this is basically the example I will talk through, but I just want to walk you through it here. sklearn, scikit-learn has a decomposition set of modules, and one of them is PCA, and it actually lets you pick, it actually lets you build a PCA with the number of components. So what this is saying is that we want to be able to compute the first two principal components for this particular data set. This is a two-dimensional data set, so obviously you can't go higher than 2, right? Then it lets you fit, okay, and it gives you the PCA components. So these are actually, right, just the eigenvectors of this data set. And it, the explained variance, okay, is also given to you by the PCA. Okay, and so one thing I wanted to note is that here the PCA actually gives you the explained variance. It's also got the explained variance ratio, okay, which actually computes the ratio of variance explained by the first and the second principal component. So we see here that 97.6% of the variance is actually explained by the first principal component. And you can probably just take a look at this and guess what the first principal component is, right? It's just going to be this this line that follows along the data. And here we can actually plot it using this nice draw vector function. And so you can see the principal component is, the first principal component is this guy. Now, the interesting thing to note is that the length of the vector, right, ax equals to lambda x. Lambda is telling us the amount of variance explained. And you can also actually picture lambda x to be, x is giving us the direction, but lambda x is giving us the length of the vector. And so the length of the vector is actually telling us how important that particular axis is, okay? And so this is just kind of a regurgitation of what I said earlier. What I really wanted to talk about was down here. Okay, PCA is dimensionality reduction. What's nice about PCA is it lets you transform the data into a lower dimensional space. So here we can see the orange points are the original points projected down onto the principal component axis. So if you're working with a two-dimensional problem, you could start working with a one-dimensional problem where these are the points that you're going to be working with. And now instead of having a two-dimensional problem, you have a one-dimensional problem, so it's easier. This is obviously more interesting when you have very high dimensional problems and you want to work with much smaller dimensions. But the nice thing is, going from the original data set to the new data set, you're only losing 3% of the variance explained, right? Because the first principal component explains 97% of the overall variation in the data. All right, so what I really want to talk about is this particular example of image data. So here, before we actually do any PCA, for those of you that haven't seen this digits data, this is kind of a simplified MNIST. MNIST is the kind of the most famous image data set, machine learning. So if you look at digits dot data, if we look at the first one, we can actually plot it. Well, actually, before we do that, just to make you familiar with the data, so we have 1,797 data points. Okay, so n is equal to 1797. P is equal to 64. This is the dimension of the data. Now these are images, so we don't want to look at 64 dimensional vectors. We want to look at a grid, and so you can actually use this reshape function to plot. Let me see. Let me call it example 1, and we want to use this function imShow. And this is just some kind of color coding, okay, and we get this image. So that 64-dimensional vector, if you reshape it into an 8x8 grid, okay, so 8x8 means 64 pixels, 8 on each row, and 8 columns of 8, then you can actually see the digit that's captured in each image. Okay, so if I change the example to be another number, say 20, we'll get another 0. Can I get a different, say 51? Okay, so 51 is a 2, and so on and so forth. So we have, a 64-dimensional data set. Okay, now PCA, choosing the number of components to be 2, we want to be able to plot each of these 64-dimensional vectors in 2-dimensional space, right? So that's a huge reduction in the data. But so let's see what that gives us. So this is the PCA function, again applied with n components equals to 2. We project the data and fit it. So fit transform doesn't just project the data, it takes the original data set and projects it onto the 2-dimensional space. Okay, so the first thing we're printing out is the original shape, 1797 by 64, and now the new shape is still we have 1797 data points, but now there's only 2 features, right? So there's only 2 dimensions explaining each image. And we have this really nice function where we actually plot component 1, component 2, so 2-dimensional space, and we plot each of the digits. We have digits 0, 1 to 9, okay? And you can see here that the principal components are actually being able to kind of separate the digits into different portions of the space, right? It's not perfect, but it's pretty amazing for going from 64 dimensions to explaining a picture, going down to 2 dimensions and being able to kind of really separate data in this way. Okay, so we can see that the 0 class is really easy to kind of project down, which kind of makes sense. It doesn't really look like a lot of other classes, or a lot of other numbers. And so we can see that it's really hard to do the say, what is this light blue 8? Seems to kind of be clustered in. It's kind of hard to see with these colors, but it seems to be really hard to distinguish the 8s. And so this is basically what PCA gives you. It gives you a dimensionality reduction from 64 to 2. Now, this is nice, and when I first saw this as a student in this course a few years back, I thought this was awesome, but I didn't really understand what was going on. I kind of just took scikit-learn to be implementing PCA, and I just kind of trusted it. Today, what I want to do is just quickly try to derive the same result without using PCA, the PCA library in scikit-learn. So what I want to do is basically take what we talked about here. Okay, we have a sample of n points. Each one is a 64-dimensional vector, and I want to try to use the eigenvalue package to try to get the same result. Okay, so let's try doing that together. So x, I'm going to call the data set, and x bar is going to be the mean, right? The mean vector. Axis equals 0, so we need the So here, just to be really clear, X bar should be a 64-dimensional object. Okay, and I'm going to call X zero mean is just going to be equal to X minus X bar. And so this is actually a subtle point. When you're doing PCA, you need to actually standardize your data. The first thing you need to do is take the mean away, okay? And you can actually see that from the way we defined the sample covariance, it's xi minus x bar, so you minus the mean. But one thing to be careful about is that, since we're maximizing variance, right? If your features are in different units, so say for example, like your first feature is kilometers and your second feature is millimeters. Millimeters are obviously much smaller than kilometers, so the variance associated to that first feature is going to be very large just by the nature of the way the units are measured. So if you have that kind of situation in your data set, doing PCA is just going to favor the feature kilometers, right? Because it's just going to get a bigger number. So in that particular case, you actually need to standardize your data to have variance on the same scale. In this particular problem with MNIST, each feature is a pixel, so we're not going to actually have that problem, right? Every pixel is within the same range of values. So all I'm going to do is just take the mean away, and then I'm going to compute S, which is 1 over n minus 1. And our sample covariance matrix is 1 over n minus 1 times the zero mean portion transpose times x zero mean. And then I'm going to actually use the eigenvalue package in NumPy that I used before for the matrix multiplication. And I'm going to write, well, let's write V for the L for the eigenvalues and V for the eigenvectors. Okay, and that's going to compute the eigenvalues. So let's see the eigenvalues. So okay, we have 64 eigenvalues, and you can see that the size is decreasing, so we're already getting eigenvalues in decreasing size. V is going to be a vector 64 by 64. So the first eigenvector is going to be, the first column of V. That's this guy. Okay. Now what I want to do is take the first two eigenvectors of V. Okay, and I'm going to call this V2. Okay. And I'm going to do the projection manually. So how do we project the data? Remember, we project the data by computing the dot product alpha 1 transpose xi. Alpha 1 is the first eigenvalue, and we can compute the projection onto the 2 points by computing alpha 1 transpose xi and alpha 2 transpose xi for all the data points. And actually, it's really easy to do that in NumPy using matrices, because it's just going to be the zero mean data times this reduced collection of eigenvectors. And we can look at the shape. Let me call this projected data. And we can look at the projection data shape. Again, we can see we have the same n and only 2 features now. So this should be the same as the projected variable here. Okay. And let me try to use the same plotting function, but with my not manually, but my variable proj data. Okay, let's see what we get. Okay, and so this is what we get here. And let's just compare it to see if I can kind of compare them on the same screen. Okay, and so we can actually see that my implementation using the eigenvalue package. Let me just push this up. That's better. So my implementation looks similar but slightly different, right? You can see that the zeros, right, the zero clause here is on top, my zero clause is on the bottom. So what's happened is actually that, the right points, the yellow points here are on the left. Okay, it seems like the image that I get is inverted, right? It's kind of upside down, and it's kind of like a mirror image. And the reason that happens is because if you go back to the eigenvalue calculations that we did here, right? We took x1 to be 1 over root 5, negative 2 over root 5, but you could have also taken it to be negative 1 over root 5 and 2 over root 5, right? You could actually switch them around, and that still gives you a valid eigenvector. So that's kind of what's happening here. The different eigenvector, the eigenvector implementation in the PCA is taking a slightly different but valid eigenvector. Maybe the sign is changing, so that's why we're getting this kind of weird mirroring happen. However, it doesn't actually make any difference as far as doing machine learning with these things. You're actually still getting the same variation explained and the same kind of segmentation of the data in two-dimensional space. The reason I wanted to do this is because I think it's really important to understand the connection between PCA and eigenvalues, eigenvectors. It's the same thing. Okay, there's nothing particularly new happening. It's just that the PCA clause is more for data science and machine learning, so it has things that are more suited to machine learning, whereas eigenvalues, eigenvectors are used all over the place in science and engineering. Okay, now finally, the number of components, we had 64 total dimensions, so you can actually plot the cumulative sum of the variance ratio, right? So, the first one explains the most, and as you keep increasing principal components, you get to the full variation being explained. And this is called a scree plot, and the scree plot is basically a way of trying to determine how many dimensions, how many components you want. You could say 80% of variation is pretty good, and we only need to maintain 12 dimensions. So PCA is giving us a way of reducing the number of features. It's also giving us features that are independent, right? Which is really nice. It makes a lot of algorithms work nicer. And so, this is the way to decide on the number of components. Very rarely do you actually need 100% of the variation explained, right? The trade-off between having 64 dimensions and full variation versus having 10 dimensions and 78% variation, based on the particular kind of field you're working in, could be quite small. Okay, and that's basically all I wanted to talk about for this lab. You will actually see another example here using eigenfaces that tries to explore the actual what the eigenvalues are. So this is different faces, and it actually shows you what the first principal component is capturing, what the second principal component is capturing. I'll leave this for you to go through, but this is nothing new. It's actually just trying to look at what we called alpha 1, alpha 2, alpha 3. It's trying to figure out what those things look like for different images. And it's basically, it's a way of trying to understand what the principal components are capturing. So the most important aspects of these photographs in this case are kind of like the lighting on the face. And as you go down to further PCs, you can see more focus on the particular features. So different noses are better to distinguish pictures, and then here you can see a little bit more focus on, I guess, the mouth, the forehead, or the eyebrows. Okay, but essentially it's kind of the same idea we've talked about already. Okay, so the next thing we were going to talk about is the k-means algorithm, and this will just be a really quick introduction to kind of a really basic algorithm that's it's pretty trivial to be honest. So I'll just write down the pseudocode for it. So it's just 2 steps. So k-means. Okay, first step is pick initial centroids. Okay, so you just have to give it a k, and let's call these guys mu1 to mu k. So these are going to be the centers. So assuming you have a bunch of data that, if you're lucky, is kind of already segmented, these mu's are going to be the cluster centers, and you just have to pick the initial value for the cluster center. So you could pick, say this is mu1, this could be mu2, and this could be mu, let's say mu k if you have k many cluster centers. And then the second step is to repeat until clusters or cluster centers don't change. The following. So for each data point, so for each I, we want to assign the cluster label, well, let me just call it CI. So we iterate through the entire data set, and for each data point, we assign a cluster. The cluster is going to be the argmin of the distance between xi and the cluster center. Okay, and here I'm using the 2 norm, but really it can be any p norm. We don't need to take the square. We can just say the smallest p norm, where we're minimizing over the j variable. So what is this? This is computing the distance of every single point in the training data to each of the clusters, and it's looking at where the data, or which cluster center is the data point closest to, and then it's assigning that as the cluster label for that point. Okay, and we do this for every single data point. And then for each j, so now we're looking at the k clusters, we compute a new cluster center, which is let me explain the notation in a minute. Okay, so this, first of all, this is an indicator variable. So this one ci equal j is going to take a value of 1 or 0 if the cluster label of the ith point is j and 0 otherwise. So what this is saying is that sum through all the data points and only count the values that are actually belonging to the jth cluster, right? So this is going to be 0 for the xi's in different clusters, and so we don't include them in this. The denominator is the number of points in cluster j. So what this is just an average of the xi's in cluster j. Okay. So in other words, the k-means algorithm is we start off with some cluster centers. The first step here is this is assignment. Okay, so each data point gets assigned to a cluster. The assignment works by assigning each data point to the closest cluster center. And then once you have your points assigned to a cluster center, then we recompute compute the cluster centers, and the new cluster centers are going to be the average of the xi's in that cluster. Okay, and we're going to keep iterating this until there's no change in the second step here in the cluster centers. So I mean, it's a really straightforward algorithm. So I've just implemented here in Python a pretty simple implementation for this data set. So this is just a random data set of points in 2 dimensions. Here is what they look like. Okay, so there's no labels. This is completely unsupervised. We have no information about where, which groups each point belongs to. Here I've got an assign clusters function. So what this function does is basically in this for loop computes the distance of each point to each center. So each center is in this cluster centers argument. Computes the distance, and then it computes the argmin for each row. So that's basically assigning each point to the closest cluster center by looking at the smallest distance to each of the cluster centers. This function, compute cluster centers, basically segments the array based on the cluster assignment, and then computes the mean over that cluster. Okay, so this is just the 2 steps that we talked about in the pseudocode, and in here I've got just 3 colors I'm using to distinguish between the clusters. I've got cluster centers, 3 cluster centers, so k equals 3, and so basically this looks like this. So this is just the initial. I've just initialized my 3 cluster centers here in 3 different colors, and I've done the first assignment step. So these red points are assigned to this cluster. These 2 purple points are assigned to this cluster, and the yellow point is the single point in the third cluster. Okay, and I'm gonna start off again with these cluster centers, and I'm gonna plot for 5 iterations what happens with the k-means algorithm. Okay, so iteration 0 is the picture we saw earlier. So what happens at iteration 1, right? So what happens to for example, for the red points? These are the red points. So we look at the average of those points, which is obviously going to be somewhere here, right? Somewhere closer to the bulk of the points. That's going to be the new cluster center. So we see the red cluster center shifting to the left. And then we also see the same thing happen to the yellow, cluster. And then we actually see something interesting happening to the 2 points here, right? They actually change assignment to the purple cluster, okay? And there seems to be a point up there that cannot actually be seen. There's a 3rd point up there as well. Okay, so in the second iteration, we do it all over again. So you can see that the cluster centers are kind of converging to the centers of the 3 clusters, and then there's no change in iteration 3 or 4. Okay, so the algorithm actually converged after 2 iterations of k-means, so pretty quick. Here I repeat the analysis, but I pick k equals 2. Okay, and we can see with k equals 2, the clusters are forced to kind of account for a larger cluster size that's kind of awkward looking as far as the shape goes, but the result is still plausible, right? It's still plausible that these purple points belong to a cluster, and these guys on the left belong to their own cluster. And finally, for k equals 4, here we have a new black cluster, and same thing happens, and you see that now you start to get these really small clusters that don't look very natural. And so I guess the point I'm trying to illustrate here is that one of the biggest problems with this algorithm is, how do we pick k? And that's a problem with the unsupervised learning in general, is how do you try to pick the variables when you're trying to find structure in the data. And so, as you increase k, the data is going to try, or the algorithm is going to try to make that particular k work for your data, regardless of what your data looks like. And so there's various algorithms of how to get around this and how to pick k and how to evaluate different metrics, but you generally have this problem with unsupervised learning of, in PCA we had it with how many components to take. With k-means, it's really how many k you're looking for.